Okay, so the next video I'm making is taking our RATEY and taking it a little step further. Obviously, we're using it for graphing. Now, I will say this. Um, what's really occurring here is we're taking these and we're trying to get a rough sketch, if you will, to produce what our graphs look like. We're not necessarily looking for exact graphs, which is more applicable than you think. You know, there's going to be a lot of different things where sometimes you just need a rough sketch, a quick little view of what the graph is going to be, or be familiar with kind of what it's going to look like, and that's going to help us solve problems later on, especially when you guys get to calculus. So I'm not necessarily looking to graph these exact, but it's just getting a good rough sketch. Sometimes they're exact, but getting a good rough sketch at times to answer particular questions later on. So don't be too stressed about finding exact points all the time. Typically, if you just follow RATEY, you'll answer the questions you're supposed to. So let's kind of dive right into it. The first thing is, if you're looking at your notes, is that you have this thing we're talking about with whole, and then we have our roots. All right, I'm just going to kind of do that at the beginning. Your asymptotes, which I'm going to kind of abbreviate here. Remember, that's our vertical asymptotes. And just continue to go down our tangency / togetherness, in behavior, and then, of course, our y-intercept, which, if we look at this front portion right here, it's our RATEY. Okay, the only thing that's added is our whole. So before you do any of these graphs, the first thing you need to do, and always need to check, is if you can take your function and factor everything. Okay, so I'm going to come down here. If you took x squared minus 9 and x plus 3, okay, that's our f of x function. We could factor that as x plus 3, x minus 3. Well, what happens is our x plus 3's will actually simplify. Okay, so the thing that would be left over is just our x minus 3. So when these rational functions simplify like this, it actually produces a hole in the graph. And it produces a hole in the graph at that specific quantity that was simplified. So for instance, what would make x plus 3 equal to 0? Well, that'd be if x was negative 3. So that means we have a hole at negative 3. And everything we do from this problem, or on this problem, for the remainder of the graph is going to be dealing with our leftover portion, our x minus 3. So if we want to figure out, well, we know the x coordinate of the hole, where would the y coordinate of the hole be in? We'll just take negative 3 and substitute it in place of x on our x minus 3. So if you will, it would just be f of negative 3. So f of negative 3 would be negative 3 minus 3, which we know is negative 6. So our hole, there's going to be a hole in the graph at negative 3, negative 6. And then from here, we'll also continue to look at it and answer the questions with the RATEY. So if we're looking at where the roots are going to be, well, for x minus 3, what would make x minus 3 equal 0? That would be if x was equal to 3. So we know we're going to have a root at 3 comma 0. All right. And then asymptotes, vertical asymptotes. Well, if you wrote this over a denominator, it'd be a denominator of 1. And obviously there's no way that the denominator can be equal to 0. So there's not a vertical asymptote. Tangency, there's no numerators that have an even multiplicity. So there's no quantity that has like an exponent that's a 2 or 4 or anything like that. Same thing with togetherness. There's no denominator that has an even multiplicity. Okay, just continue on. In behavior, okay, now in behavior, technically speaking, this has a degree of 1 on the top, and this one has a degree of 0. So you could do like the long division, but if you were to divide x minus 3 and 1, well, you would get x minus 3. So you could think of our end behavior being y equals x minus 3. That's a bit trivial, but it's something we'll go ahead and list just to be consistent. You'll see a better application of that later on in this particular video. And that's probably hard to see that, but we divide that x minus 3 by 1. And the last thing is our y-intercept. So we want to determine our y-intercept. Remember, that's where we plug in 0. So we're going to plug in 0 for our x minus 3 right here. So 0 minus 3. We know we're going to have a y-intercept at 0, negative 3. So we have a lot of information here that we can work with. So now when we come over here to produce our graph, all right, we know we're going to have a hole at -3, -6, roots at 3, 0, in behavior, and our y-intercept. So we want to go ahead and plot our y-intercept. And I'm just kind of doing this by hand. Obviously, or hopefully you can maybe print off the notes and you can just count them off and go through it like that. But I think you'll get the general idea, hopefully still, of what's going on. So 0, -3, we're going to have a root at 3, 0. So I like to plot those 2 points first. All right, and then we're going to have a hole at -3, -6. So down here we have a y value of 6. And there's going to be a hole in our graph right there at -3, -6. And from here, that's good enough for me. If you want to go ahead and plot it, it's just going to be a line with the hole. And then in behavior, it's approaching y equals x minus 3. Like I said, that's a bit trivial in this case, but this would be our graph. And that's the basic form of a rational function. It's just a simple line with a hole in the graph. All right. So our second one. Let me do this. I'm going to try to be a little more efficient. I'll pause this and I'll be right back. All right, so I went ahead and wrote number 2 in. But before we go to number 2, I kind of scribbled in. If you look right here, we have a limit as x approaches negative infinity for f of x and positive infinity for f of x for our graph. If you just looked on the notes, that was also something I need to make sure I answer with you. And so as we go, it's just really talking about in behavior. As x goes to negative infinity, then our y values are approaching negative infinity. And as x approaches positive infinity, our y values are approaching positive infinity. All right, so now, number 2. So the first thing we do is look to factor it. Okay, everything's factored. The next thing we see if we can simplify anything, determine if there's any holes. Okay, so there's no holes because nothing simplifies. So next thing we do is look at roots. What would make our numerator equal to 0? What would, well, the x minus 3, a y x value of 3 would make our numerator equal to 0. And for the x plus 2, -2 would make our root equal 0. Or would make a root of -2, which would produce our numerator equal 0. Okay, so now we're looking at vertical asymptotes. Okay, so our vertical asymptotes, x equals 2 would make this quantity equal 0 in the denominator, and x equals -1, let's put a comma there, would make that particular quantity equal 0. Tangency togetherness, there's no even multiplicities, so there's nothing going on there. In behavior, well, if you were to take this entire numerator and expand it out, you would get an x squared as your leading term in its degree. And then this would also be an x squared. Okay, so just to make sure you have a visual, this top will become an x squared, whether it be minus x minus 6. And this one would become x squared minus x minus 2. And the leading coefficients on both of these are 1s. So we would take a ratio of those coefficients, which is 1. Since the degrees are equal, they're both 2s. So our in behavior would have y equals 1, which would be a horizontal asymptote, since those are equal in this particular case. Then our y-intercept, we're going to plug 0 in for x. So if we were to plug 0 in for x, you can work that out. You would see that you would get 3 for your y base. So that's just plugging 0 in for x and our original f of x. Remember, because nothing simplified this time. So we have a bunch of points that we can plot. We have -2, 0. We have 3, 0. 0, 3. All right, so we have all those points plotted. Those are our roots and our y-intercept. We have some asymptotes that we can also put into this. So we would have a vertical asymptote at x equals 2. So I'll just draw a dashed line so you can kind of see that. So at x equals 2, we're going to have a vertical asymptote. And at x equals -1, we're going to have a vertical asymptote. Okay, and then the last thing we have is this horizontal asymptote at y equals 1. So let me draw that in there. So these dashed lines represent our asymptotes. We have 2 verticals and a horizontal. So what I like to do when I'm doing RATEY is just, if you think of these vertical lines dividing our graph into three sections, you have this portion on the left, the middle portion, and then our right portion. I like to get this middle portion first, because what it does is once I get these middle portions, sometimes more than one, but in this case, just one, once I get that middle portion, it'll lead me to figure out what the other two pieces look like. So we know that obviously our graph's gonna go through this y-intercept. It is possible for a graph, for instance, say our graph is going like this. It could go through this point and go past, or through rather, the horizontal asymptote. Okay, because the horizontal asymptote, remember, it has to do with end behavior. It's what's happening at the end of the graph. So it is possible to go and intersect in horizontal asymptote. Only thing is, we also know, but we do know it's not going to go below the x-axis, because if it did, then we would have had another root that would have been accounted for. So this graph is definitely going to have to pop up at some point. Now, if we want to double check that, we're more than welcome to. So we could plug in values of x, and really this middle section, just kind of put it right here. Let me go off to the side. There's four types of graphs you're gonna be looking at right there. You could have, well, they're not parabolas, but they kind of have an appearance sometimes of being parabolas. But these U-shaped graphs, you could have those be in the middle, or you could have something like these. You might think of them as being cubic, but once again, they're not necessarily cubic. So these are our four choices of what they look like in this middle portion. So for this particular one, if you're not sure, you can take f of 1, you can plug it in and kind of see where that takes you. You could plug in, f of 1.5. You could plug in f of negative 1/2, all those different things, and you can figure out what's going on. Now, since it's not going to go through the x-axis, we know that these two are out. All right, because otherwise these two situations would produce another root. So now we're just down to these two parabolic, if you will, looking figures. So it's going to be going up or it's going to be going down. Well, if it was going down, it would also be producing roots again. So this one's out. So the only one that remains is it's going to look something, okay, just like this, okay, passing through our y-intercept. And that tells us a lot of information, because say I was looking over here on the left side of this graph now, okay, we know, or I'll just take these, the left and right are going to be similar. So over here on this outside, when we have these asymptotes, you have things that might look like this, or it might look like, the other way around, like that. Okay, there's different situations. So what we're looking at now is it's going to be something that's approaching a horizontal asymptote, because that's what our end behavior is. The only thing we're concerned about is it coming up here? All right, so I'm just going to say, does it look like this on the top, looking over here on this right, or is it going to be down here, looking like that? Because both of these situations would produce a graph that approaches this horizontal asymptote. Well, you probably already see some things. If it was this graph, if it was this one that was coming up and then going down, the problem is if we were to take this and slide it in, if you will, and put it right here in this particular graph, that would mean we would have togetherness at this vertical asymptote. We don't have for togetherness. We've already talked about that earlier, because we had no even multiplicities, which means that our graph has to be coming from down here. So the graph has to be going this direction. We have to capture our x-intercept, our root, and then it's going to flatten back out at that horizontal asymptote. Okay, and the same argument applies on this left side. We want to know, is the graph up here and then coming up to that spot, or is it coming from down here? Right? Is it going over and then going down? Well, they're not. This one's going to infinity, this one's going to negative infinity. Or is it both going to infinity? Well, we don't have even multiplicity. There's not a togetherness aspect. So once again, we have a graph that looks like that, just like on the right. So here's our finished product. You have this left side portion, we have our parabolic, if you will, figure, and then once again, there's our finished product for our rational function. And as we do more and more of these, you'll see kind of the pattern that develops. Now, just to kind of, again, if you have questions on this, do not hesitate to ask me. I'll go over this again. Not being in person hurts not having these discussions, but hopefully I'm able to give you a good foundation at least. So now to answer these limit questions. As x approaches -1, so remember -1 is this vertical asymptote right here on the left. So this negative where my pen's highlighting right now, up and down. So this -1 from the left. So as x approaches -1 from the left, we're going really down here to -infinity. That's the y value we're approaching. As x approaches -1 from the right, so we're on this parabolic, if you will, looking figure, it's going to go up all the way to positive infinity. Remember, if it was both infinity or both negative infinity, then we'd have togetherness, but they're different ones. They're negative infinity and positive infinity. Do the same thing for 2, our other vertical asymptote. As x approaches 2 from the left, okay, remember from the left, so I'm coming from the left to the right here. On our graph, it's going up to infinity. All right, and as x approaches 2 from the right, so here's our vertical asymptote. As x approaches 2 from the right, it's approaching -infinity. And then our end behaviors, as x approaches -infinity, way over here, we're going to 1. And as x approaches positive infinity, we're going back to our horizontal asymptote again. It's going back to 1. All right, next problem, number 3. There's no holes. Remember, we've factored everything. There's nothing that can simplify. We're looking at roots. So we know that if you put a 1 in place of this x right here, that would produce a root of 1, 0. And then a -4, 0 would occur with that x plus 4. We're looking at our vertical asymptotes. 2 are here would make the denominator equal 0. That would be if x were 2. So we're going to have a vertical asymptote at x equals 2. Togetherness. We do have some togetherness. No tangency. There's no even multiplicities in the numerator. But right here in our denominator, we have a square. So that means that we have togetherness at, let's go togetherness at x equals 2. So it's going to be togetherness at our vertical asymptote. In behavior, this would produce a 3x squared in the numerator as our leading term, and this would produce a 1x squared for our leading term. So 3x squared and 1x squared, that means our in behavior would be y equals 3 for our horizontal asymptote. Okay, and then our y-intercept, if you plug 0 in place of x and solve all that out, you would get 0, -3. So we can plot these points. 0, -3, 1, 0, -4, 0. All right, we're going to have our vertical asymptote at x equals 2. Oh yeah, got the crayon for our vertical asymptote. That's the one, that's the one. All right, so now we know vertical asymptote at x equals 2, and we're going to have a horizontal at y equals 3. Cool. So now we have this graph. This one's a little different because we actually have togetherness now. And we have this horizontal asymptote. So everything right here, it looks like on this left side of the graph is quite a bit is below the graph. So we know that out here to the far left, that our graph is going to be approaching this horizontal asymptote. And then it's going to have to somehow capture this point, capture our y-intercept, and then come back up and capture this x-intercept. So this is probably, to me, this is probably the oddest graph of the bunch, but it's going to have that right there. Right? There's our horizontal asymptote. It has to come down here and capture this point. It's going to curve over here. It's going to hit our y-intercept. We have to get back up here and hit our x-intercept. And I'm going to stop here just for a moment. It's not going to hit this and come back down, because that would mean that we would have tangency, and we don't have tangency. It's not going to come back up here and then come back down, because then we would have another x-intercept to account for. So this graph has to continue to move on. With rational functions, these always go. So this is going to continue to move. And remember, it's okay to go past a horizontal asymptote, because the horizontal asymptotes only deal with end behavior. It's just what's happening eventually at the very ends on the extreme left and extreme right. Now, this is the left portion. Now we look over here on our right portion. We don't have any other zeros. So there's no graph that's going to be approaching on this bottom portion. Otherwise, we'd have another 0. So our other portion of our graph is going to be up here. And we talked about togetherness with x equals 2. So there's going to be, our graph is going to be coming together right here at this particular spot. And just for right now, like I said, we're looking at rough sketches, not exact, so you don't have to find those points. That is good enough for me as far as getting a rough sketch of what our graph's going to look like. It's going to be come together at that vertical asymptote and approach that horizontal over on the right. So looking at our negative infinity and positive infinity, looking at our extremes for our horizontal asymptote. Once again, we know that's going to be 3 for both the negative infinity and positive infinity. And then as x approaches 2 from the left, as x approaches 2 from the left, it's going all up to infinity. As x approaches 2 from the right, it's going up to infinity. All right, our fourth graph we're going to look at now. Just run through it again. There's not any holes. Although I probably should just make sure we do go ahead and factor it like I said earlier. So this is the same thing as x cubed over x plus 3, x minus 3. But nothing simplifies there. Okay, our roots and the numerators are origin in this particular case. So 0, 0 for our asymptotes. X equals 3 and x equals -3 would produce vertical asymptotes. For our tendency togetherness, there's no any even multiplicities. For our end behavior, so I think I can fit this over here to the right. So we would have x cubed and x squared minus 9. So since our numerator degree is 1 larger than our denominator degree, we do long division to figure out our end behavior, which we know this is going to become a slant asymptote. So you can put this as 0x squared, 0x, and just fill it in if you will. But it's going to fix itself pretty quick. When that x squared would go into x cubed x times, so we'd be saying minus x cubed, and what is that going to be? Plus 9x. So I'll put that under the x's. So we would have a 9x right there. And you can bring down the 0 if you want. But I don't really care about the remainder here. The only thing that we're looking at is we're going to divide this out as far as we can, which is this is done. This is as far as we can do it, because typically we now take our remainder, and we'd write that as our plus 9x over x squared minus 9 as the finished quotient. But we only care about the initial division. We don't care about the remainder. So this x right here is going to be our end behavior. So y equals x, which obviously is not our nice y equals a number horizontal asymptotes that we've been dealing with lately. Now it's going to become a slant asymptote. And then our y-intercept, and if you plug 0 in for x, I'm sorry, if you plugged it in for your y, if you determined your y-intercept and just went through the whole process, you find that that's going to be a 0, 0. All right, so looking at our graph now, 0, 0 is a point. All right, that's the only point that we have. Okay, then we also have our vertical asymptote, and that's at x equals 3. And -3. Okay, so we got both of those drawn in. And then we also have this y equals x for our slant asymptote. All right, so that's going to be just the line that you've always dealt with, slope of 1, going through the origin. And so y equals x, this would be good enough for our purposes right now. It's going to go across our graph like that. All right, so we have these 3 divisions once again. We haven't ran into this situation since earlier, And remember, we always like to start with this middle section, and we're thinking this middle section could be, 4 choices. Okay, that's one of our 4 choices right there that we could be working with. And let me draw those actually, we could see them. I apologize. Let me try it down here. So our middle section, remember, it could be one of those 2, or it could be something like that. Okay, so it's one of those 4 choices. Obviously, it's going to have to go through our x-axis right here. So it could be these, all right, but then it had to bounce because there's only one x-intercept. So these are both out, all right, because bouncing and then coming back up has to go probably through that. You can even think of this as being this odd. We don't have that even multiplicity that would make a bounce. So it has to be one of these right here, these snake-like figures. It's just a matter of figuring out, is it the one on the left or is it the one on the right? All right, so to figure that out, it's just kind of basically plugging in your points. You could plug in, 1 for the x value, and then you can plug in 2 for the x value. So say I plug in 2. If you plugged in x value of 2 into our original function, move it up where you can see it, that'd be 2 cubed over 2 squared minus 9. So we write that over here. So f of 2 would be 2 cubed, which is 8, and then it'd be 4 minus 9, which is 5, but it's going to be a negative, isn't it? So since it's a negative 5, we know that 2 and negative 8/5, which is just a little bit less than 2, but it's somewhere down here, our graph. Okay, and then if we were to plug in negative 2 would produce a negative 8 on the top, and it produces a negative 5 on the bottom. So now it's going to be a positive 8/5, so it's over here somewhere. So now we can see our graph is going to be the snake figure that looks like this. So there's our middle portion of our graph. And once again, remember, it wasn't the parabolic ones, because if it's parabolic, it would go down, it would touch that graph, and it would pop it back up, it'd bounce, if you will. So we know that that's the particular graph. In this case, it doesn't work. So it has to be the snake graph, I'm sorry. So now we're looking at these outer portions, this one on the left and this one on the right. All right, so we're looking for togetherness. Nope, no togetherness. So we know there can't be anything over here on the graph, because otherwise the graph would kind of go right here. It had to follow this slant asymptote, and it would bend up, and it would end up right here, but there's no togetherness. So that means that it has to be down here in this bottom portion instead. So our graph has to be going along that asymptote, and it also has to be going along that part of the vertical asymptote, since there's no togetherness. So it's just this little shape right in here that's going to squeeze in. It would look like that. And again, I don't care about points. We're just looking for those rough sketches again with RATEY. And I'm going to do the exact same approach over here. Kind of took it up with my writing, but this graph does not have togetherness. And there's no denominator quantity that has an even multiplicity, so there's no graph that's down here. Okay, the graph has to be up here. It has to be going up. All right, and then if it's coming from this direction, then it's going to hit this, and it's going to have to go along our slant asymptote and then go over here to the right. So we have this little portion right down here. You have this little snake in the middle, and then we have this little portion up here with its vertical and slant asymptotes as well. And the only point that we had here was our y-intercept, right? So that's when if you plugged in 0 for your x, and you were to look at that, you would get 0 cubed over 0 squared minus 9, which is 0. I haven't really said that specifically, but just wanted to make sure this is a good problem probably to say it on. That's why our y-intercept is 0, 0. All right, so there's number 4. Next one we're going to look at is number 5. Now, before we run to number 5, make sure we also get these limits. I apologize again. So our limits, as x approaches negative infinity, as you get really extreme out here to negative infinity, the y value we're getting close to is negative infinity. And as x approaches infinity, as we get really far here to the right, our y value is going to infinity. Now our negative 3, okay, that's our vertical asymptote right here. As we approach negative 3 from the left, from the left, our y value is approaching negative infinity. And as we approach it from the right, you approach negative 3 from the right, it's going up. So that one's going to be positive infinity. All right, so now the last one's our vertical asymptote at 3. As you approach 3 from the left, it's going to be going to negative infinity. And as you approach 3 from the right, okay, so here's our vert 3. There's 3 from the right. As you're getting really, really close to 3, we're going up. So that would be our positive infinity for that particular limit. All right, let me turn the page here. Okay, now we can do number 5. So number 5, it's all factored, nothing to simplify, so there's no hole. Looking at our roots, we know it's going to be at negative 2, 0 for our roots. Vertical asymptotes, we have x equals negative 1, x equals negative 3, and x equals 2. So we have 3 vertical asymptotes in this problem. Tangency and togetherness, we do have tangency this time. Okay, so we have tangency at this particular spot. Let me highlight that a little better. There we go. So we know we have an even multiplicity at the top. So tangency is going to be at x equals negative 2. All right. No togetherness because there's no even multiplicity in the denominator. In behavior now. All right, so we're looking right here. The top would produce an x squared. Okay, for our leading term would have an x squared. The bottom, if you were to expand all this out, if you multiplied x plus 1 and x plus 3, you get an x squared. And if you took that and multiplied it times x minus 2, you would end up with an x cubed. So you have x squared dot dot dot, right, on the top. And you have x cubed on the denominator dot 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 with various terms. So if you're looking at that, we're bottom heavy. Since we're bottom heavy, we know that our end behavior would be y equals 0 for our horizontal tangent, or horizontal asymptote, I'm sorry. Horizontal asymptote. All right, and then our y-intercept, if you plugged in 0 to all of these different pieces, for the x, this would produce 0 plus 2 squared, 0 plus 1, 0 plus 3, 0 minus negative 2. If you did all those and you calculated it out, 0, negative 2/3. And I know you guys have done this a whole bunch, and I hope you don't think anything as far as me skipping that step. I just know you've done that a whole lot throughout math, and that's just kind of saving a little bit of time on the video. But if you need me to go through that in more detail, please don't hesitate. I'll go through it. If you have a question, let me know. So let's see here now. We have a root at negative 2, 0. All right, so plot that point. Try to let that video catch up. Good. All right, so now we're looking at our vertical asymptotes. We have one at negative 1. Let me draw that in. All right, we have one at negative 3 as well. So draw that vertical asymptote. And then we have one at 2. X equals 2. Okay, and then the last thing we have as far as our asymptotes are concerned is a horizontal asymptote at y equals 0. So it's just our x-axis. All right. And then we know we have a y-intercept at 0, negative 2/3. Let me throw that one in there. Okay, and I think that's all the information we can pull from all that. So now we're just looking at interpreting everything we can with the data. And like I said, we always start in the middle. So I'll start in this middle portion right here. This right here is our root at negative 2, 0. So we know the graph could be coming up through here and going through it, or it can come from down here and going through it, or it could be a parabola coming down and touching it and going up, or it can be parabolic, if you will, touching it and going down. Great thing about it, we know it's not. So let me just drop those little options out here again. I know I've done it several times now, but I want to make sure I'm reiterating it. So we know it's one of these 4 choices in the middle. Since it's tangent, since it's an even multiplicity, all right, it's going to have to bounce and then go back up, or it's going to have to bounce and go back down. So that one and that one are out because those would be going through the x-axis. So now we're left with these U-shaped graphs. So it's either going up and then coming back down. So it's up here, it's bouncing and coming back down, or it's going to start from up top, hit the graph, and then come back up. So it's one of these two choices. And the way we can kind of figure that out is to take values of x and then plug them into our f of x function. So you could take something like, this is what, -1, so -1.5, and we can evaluate f of, let me write it, see where I can write this, f of -1.5 and f of -2.5. All right, obviously you can write those as fractions, but I'm just kind of making it where you can see a little better right now. If you plug those in, and I know you can look at it into our original function. Okay, what you're going to do is you're going to come up with positive y values for those answers. All right, you can see right here, you plug in -1.5 into this top right here, that's going to be something squared, so it's going to be positive. You have a -1.5 with the 1 and a -1.5 with the 2. Those are going to produce negatives, but two negatives make a positive. And then times this -1.5 plus 3 is going to make another positive. So it's going to be a positive answer. Same thing with the -2.5. So these points are somewhere, up in here, which means our graph is going to be up at the top and not below the x-axis. And just for time purposes, to keep this video a little bit more concise, I went ahead and just did it that way, but you can evaluate these points and you'll see it very quickly. It has to be on the top portion and not the bottom. So from here, this helps us a lot because we have the tangency we accounted for, but we don't have togetherness. So now we're right here in this other middle portion. So we have a graph that has to hit our y-intercept, and it cannot go through the x-axis because that would produce another root. So it's down to those four choices again. And you think, well, maybe it's up here. Well, it can't be up here because that would be togetherness, and we don't have togetherness. So that means our graph has to be approaching the asymptote down here. So we know it's coming from down here. So the question is, does it come up here and go through, or does it come down here and pop back down? And like we discussed before, it doesn't have another root. So we know it's going to have to finish down here. So it's going to come up here. I don't really care if you found the exact spots like we talked about earlier. It's just kind of good rough sketches to give us a quick visual of what the graphs will look like. So now we have the middle portions taken out. So now that we have these middle portions taken out once again, sorry I had a little glitch in my video, we can start looking at the outer portions. All right, so first thing we're going to look at is the left side. All right, we don't have any togetherness, so the graph can't be coming up here. All right, so that means that the graph has to finish at the asymptote down here. All right, and we know that we have this horizontal asymptote of y equals 0. So it's going to be going like that. Okay, we'll do the same thing on the right over here. It can't be coming down here because there's no togetherness. So it means our graph has to finish on the asymptote up there, or start if you will. Okay, and then it's going to be going down, and it can't go through the x-axis because there'd be another root. So it's going to just approach the horizontal asymptote of y equals 0. So then it's just a matter of filling in our limit statements once again. As the limit goes to negative infinity, we know that we're going to, so as x approaches negative infinity, the y value that we're approaching is 0. And as x approaches positive infinity, the y value that we're approaching is 0. It's just our end behavior limits approach infinity. All right, so here's -3 right here. As we approach -3 from the left, as we approach -3 from the left, the y value that we're getting closer and closer to is infinity, or negative infinity, sorry. And as x approaches -3 from the right, the y value that we're getting closer and closer to is positive infinity. All right, as x approaches -1 from the left, we're getting really close to the y value of infinity. As x approaches -1 from the right, so from the right, the y value that we're getting closer and closer to is negative infinity. Okay, and our last one, as x approaches 2 from the left, we're going way down there to negative infinity. And as x approaches 2 from the right, we're going to positive infinity. So we have 3 more examples, number 6, number 7, and number 8. What I'm going to do is I'm going to make a separate video for those. I think it'll be a little bit easier in a different format for my explanation and how it's concerned. Like if you look at those particular ones in the example, it's not graphing like we just now done. It's actually, you're given the graph, you're going backwards, and you're determining the equation that could produce that graph. So I'm going to show a separate video on that. Just want to make sure I conclude this, and I'll post this video along with part 1 and then part 3 all up on Canvas. So you'll see those momentarily.